everybody, it's video note 7.2. We're going to talk about heat transfer and calculations. So make sure to read chapters 10 and 14. So substances change temperature differently depending on their identity. So each substance has, pure substances have what's called a specific heat or specific heat capacity. And the units are calories for every gram degree Celsius, or we can use joules for every gram degree Celsius. So I want you to think about cement versus grass. Where would you rather stand? Probably on the grass, because the cement has a lower specific heat, so it takes less energy to change its temperature, so the heat transfers to you faster. If you have a metal oven, would you rather put your hand in the oven or on the rack, or grab that? Well, you probably just put your hand in there, or neither. Hello, but the metal transfers heat faster into your skin because it has a lower specific. Okay, so talked about this in the last video, so make sure that you know the difference between heat, which is transferred energy from hot to cold substances, using these units, and then temperature is average kinetic energy due to particle motion, and is measured in degrees Celsius, Fahrenheit, or Kelvin. Okay, so what kind of data do we need to start being quantitative about this heat transfer stuff? Well, look at this. This is from that pink data table that you already have. Oh, and look, there's more. Okay. So we need to know how to calculate heat during a phase temperature change. So when do we use this equation? When there's a single state of matter, so on a slant. Single state of matter slant line. Okay. So what are the variables? Q is heat, and heat is measured in calories or joules. Calories or joules, and then calories CAL, joules J. M is for mass. Mass is measured in grams, and the symbol is G. Okay. C is the specific heat capacity, or specific heat. Sometimes we say capacity, sometimes we don't. All right. And it's measured in what we saw in the last slide, but joules per gram degree Celsius or calories per gram degree Celsius, so that we can compare different things. So this number will be different for every gram degree Celsius depending on the substance. And delta T is the change in temperature. And that is, you have to take the difference. So you're going to have two temperatures, temperature 1 and temperature 2, and then subtract. Highest from lowest. Always do big minus small, and you'll be safe. Okay, so let's use it. So 15.7 gram sample of iron absorbs. So before we even try to calculate, let's make a graph. Okay, the substance is iron. The temperatures are 25 degrees C and 175. And then I go look on my pink data sheet for iron. Oh, let's see, find iron. Is iron even on here? It doesn't matter, okay, because what it tells you is that the temperature goes from 25 to 175. And I know iron's going to stay solid that whole time because I know a lot about iron, and so do you. So what is the specific heat capacity of iron is what you're trying to find. So it's a slanted line. We're going to use this equation, Q equals MC delta T. It's not going to change phase, so we only need this. Q is this, Q, because this is joules. So I have 1086.75 joules. Okay. M is mass. There's mass. So mass is 15.75 grams. Okay. C is what we're looking for, specific heat capacity. And 175 minus 25 is the delta T, and that's degrees Celsius. All right, so let's see what happens. We need the C, so we got to get rid of the 15.75. So this is math time. Woo! And we got to get rid of 175 minus 25, which is 150. All right, so I just subtracted those. All right, this is 150. So look, so this gets rid of that. This gets rid of that. But then we got to do it on this side. So we need the 15.75 grams and the 150 degrees Celsius. Notice all our units are still going to be there. Joules per gram degree Celsius is equal to C. And we just this divided by that, and we get 0.46. 0.46 joules per gram degree Celsius is the specific heat capacity of that iron. Woohoo, yay us. Okay. Calculate the heat change associated with cooling 350 grams of aluminum from 70 to 25 degrees. Is the change for aluminum exo or endothermic? Okay. So let's make a graph. Please, please, please make a graph, because then I'll help you decide what to do. And so this is degree C, degree C. All right. So what do you think about aluminum? Well, I think you know, but 70 degrees is below water's boiling point and 25 is about room temperature. So aluminum's going to be solid this whole time. And it is cooling, so this goes down. It's a slanted line, meaning I can use Q equals MC delta T to solve this problem. Okay, so Q is the heat. Calculate the heat. So Q is what I'm looking for. M is the mass. M is 350 grams. All right, C is a specific heat of aluminum. Now, I don't see it in the problem, but lucky I got me a data table. Look at that. And on this data table is aluminum, and the specific heat as a solid is 0.92 joules per gram degree Celsius. Okay, yeah, I remember now. 0.92 joules per gram degree Celsius. And then delta T is the difference in temperature. Temperature, 70 minus 25 is 35 degrees, 45, come on, Harbin, 45 degrees Celsius. Okay, what do? I plug and chug 350 grams times 0.92 joules per gram degree Celsius times 45 degrees Celsius. Hey, look what happens. Grams cancel grams, woohoo. Celsius cancels Celsius. We're trying to find Q. Q is heat, and then so we multiply all these numbers together, and we get 14,490 what? Joules of heat. Okay. Is this change for this aluminum exo or endothermic? Well, the temperature went down, so the aluminum released heat. So it's exothermic releasing heat. Okay. How do we detect heat transfer? So you hold the ice cube in your hand, the heat from your hand goes into the ice cube. All right. So the heat's going to cause something to happen to whatever it's transferred to. Sometimes it's going to change the temperature of the other thing. Sometimes it's going to change the phase. Sometimes it could do both, change temperature and phase. But the heat loss from one system equals heat gain from another system. So this key idea is going to help us because whatever Q goes out of something, it's the Q that goes into something. And we know how to find Q. Okay. So calorimetry is a technique. And what a lot of times what happens or what could happen is you take a hot piece of metal and you put it into cold water inside a calorimeter. So what's going to happen to the metal? All right, so let's talk about the metal. It's a hot piece of metal, so metal at a high temp. Okay, so metal high T1, and then it's going to go down to T2 when you put it into the water. The metal's going to lose heat, but probably not change phase. What's going to happen to water? Well, water, a lot of times will start at a low temp, and let's just say T1 for the water, and it's going to end up at T2, and the water's temperature is going to go up. What's cool is that how do you know the heat is done transferring is when the temperature, so the water gets warmer and the metal gets cooler till they have the same end temp. That is a key. At the same end temperature, you know that heat transfer is done when the temperature stays constant. So here's the piece of metal in there, and then when the metal transfers the heat to the water takes in the heat, but then the temperature of the metal and water together stops changing, and that's the final temp. So the final temp of the water is the same as the final temp of the metal. So, okay, so this is, let's call that A, we'll call that B, but T2 is the same. What the water goes up to is the same as what the metal goes down to. Okay. And why does the temperature change? Because the heat's lost by one being gained by the other. Okay. So here's a picture of a calorimeter. Ooh, look at that. Okay. So they do a chemical reaction maybe inside of here. The heat from the chemical reaction is transferred to here. Or if it's an endothermic reaction, then heat from water is transferred into there. They can measure the temperature change of the water and then calculate the heat transfer. So here's some data that you might be able to get. Here's data for water. Here's data for metal. Metal and water got put together. Okay, so let's draw a little graph for water. Water's temperature, let's see, it goes from 20.1 degrees up to 24.1 degrees. Okay, so this is the water graph. Water. All right, let's draw a graph for the metal. Okay, metal's temperature starts at 98.9 degrees and ends up at 24.1. What? What are you talking about? That's the same as that. Right, because the final temperature is the same for both. All right, and that's the metal losing heat. Okay, so metal. We don't know what that metal is. All right, so this is a slanted line. So we have Q for water equals the mass of water times the specific heat of water times the temperature change of the water. Q for the metal equals the mass of the metal times the specific heat of the metal times the temperature change of the metal. So the key idea to calorimetry, key idea, Q metal, the heat lost by the metal is gained by the water. Okay, so that means the mass of the water times the specific heat of the water times the temperature change of the water equals the mass of the metal times the specific heat of the metal times the temperature change of the metal. Get out of town. No, stay here. Okay, so we have 37.5 grams. We have specific heat of water is 1 calorie per gram degree Celsius. We have the temperature change of the water is 4.0 degrees Celsius. Okay. That equals the mass of the metal is 86.2 grams times the specific heat of the metal. Wait a second. We don't have it. We could put C. And the temperature change of the metal is the 98.9 minus the 21.4, means you get 74.8 degrees Celsius. So now all we have to do is divide by 86.2 and 74.8 on that side, and then divide 86.2 and 74.8 on this side. That's grams, that's degrees Celsius. Goodbye, 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 goodbye. The only units left are the calories per gram degrees Celsius. That's going to be C. And then we do the math on that, we get 0.023. So specific heat of the metal is 0.023. Yay, calorimetry. Okay, let's do another one. Oh, yeah, please. Okay, another one. Here we go. All right, in this one, 350 grams of a metal. Okay, this is the mass of a metal. With the specific heat of okay, so it's the specific heat of a metal. At 100 degrees, it's placed into 450 grams of water. So this is mass of water. At 22 degrees, what is the final temperature of the system? Okay, so let's see what happens to the metal. Metal starts at 100 degrees. Okay, and metal ends at, we don't know, because that's what we're trying to find out. So metal's temp is going to go down. It's probably not going to change phase. Okay, so this is metal. That's what happens to the water. So the water temperature starts at 22 degrees. What's going to happen to the water? Well, it's going to take in heat, so its temp's going to go up, and it's going to get to the same temperature that the metal goes down to. So this is the water's graph. Okay, so heat from here equals heat from there. So Q equals MC delta T, and that equals the Q of the water, that's the metal, which is equal to the MC delta T of the water, okay? But in this case, we're going to set them equal, but we have to figure out the delta T part. So we have MC, let's do the temperature change. The metal goes from 100 degrees down to X, all right? Over here, and this is all about the metal still, we have the mass of the metals, mass of water, specific heat of water, and then water's temperature is going to go from whatever, the difference is X, so I always do big temperature minus small temperature. Water's temperature ends up high but starts low, so to keep these both positive numbers, we got to do bigger minus smaller for temperature. Bigger minus smaller for temperature. And then we plug in the stuff. So we got 350 grams of the metal. We got specific heat of metal, 0.107 calorie per gram degree C. And then we also have the temperature change of metal, 100 minus X. Okay. And now the other side, mass of water is 450 grams. Now specific heat water is not in the problem, but we can look it up, 1 calorie per gram degree Celsius. And then we have X minus 22. So now we have to do all this math and solve for this X, okay? So this is where your algebra skills come in. Fortunately, you have algebra skills, yay. So you have 350 times 0.107, and that gives us 37.45, all right? And that's times 100 minus X. So now we got to distribute that in. So we got 3,745 minus 37.45. All right, on this side, we got 450 times 1. Okay, that's 450. So we have 450x minus 450 times 22, which is 9,900. Okay, so then we bring the 9,900 to this side, bring the 37.45x to that side, and eventually we find out that X equals 13,645 divided by 487.45. Okay, and so X is going to be 27.99 degrees Celsius. So that's going to be the final temp. That's what the water goes up to. That's what the metal goes down to. Use your algebra skills to see if you can finish solving that, because you'll have to. Okay, what if we have two liquids that transfer heat? Same thing. One liquid loses heat, one liquid gains heat. So what will the temperature of the what temperature will be the final for the whole system after you mix them together when you add 35 grams of water at 88 degrees to 125 grams of water at 10 degrees? Well, think about it. What's going to happen to the 35 grams? Its temp's going to go down. What's going to happen to the 125 grams? Its temp's going to go up. So we have graph of water, let's call it water 1. All right. So water 1 starts at 88, and it's going to go down to, we don't know. All right. What about water 2? Water 2 is going to start at 10 degrees, and it's going to go up to, well, we don't know. All right. So we know that the final temp is going to be equal to X is going to be the same for both. Okay. So then we're going to Q equals MCAT this, because it doesn't change phase, and Q equals MCAT that, MC delta T, and then plug in the right things. The thing you have to break out here is that 88 minus X is going to be that temperature change. And then the mass, 35 grams. And then specific heat is 1 calorie per gram degrees Celsius. And this is going to be degrees Celsius. On the other side, this water's temperature is going to go up, and that was 125 grams. It had a mass, that was its mass. Its specific heat is 1 calorie per gram degrees Celsius. And the temperature change is going to be X is the bigger, minus 10 is the smaller. Okay, so you break this out and you solve for X. Make sure you can do the math. X is 27 point, and I'm going to write it all out so that 0625 degrees Celsius. Degrees Celsius. So that's what this is going up to, and that's what that's going down to. Okay, do the math to make sure you can. All right, make sure you read chapter 10 and 14 in the book, and then make sure you can draw graphs, know what heat is, know what Q equals MC delta T means, and that most of the time we can add up the heat from, not add up, multiply the heat for lost for one thing and find out heat gain from the other. Know it, use it, love it. Okay, that's about it. Peace out. We'll talk.